All right, law of cosines. His are a little bit. These respective formulas are a little bit lengthier than the sine. The law of sines formula. That one was pretty easy, right? Sine A over A equals sine B over B equals sine C over C. Right? You just need to remember sine and ABC. That's all you need to remember about the laws of cosines. But for the law of I'm sorry, for the law of sines, but as the law of cosines, um, the formula is a little bit lengthier, as we can see here in slide 5. I just wanted to take a look at the objectives here. So, very short section, law of cosines, and then we'll see how to find the area of a non-right triangle. So, let's take a look at law of cosines, we see here on slide 5. It says the law of sines cannot be used directly to solve triangles if we know two sides and the angle between them, or if we know all three sides. So again, that what they're talking about is what they're referencing from chapter 6.5. Those cases. So they're talking about how case C here, C and D. This is from 6.5. What I just pulled up right now. This slide 6 is different, right? Because it's from the previous section. So they're talking about if we have the other two cases, the side angle side case and the side case. Now recall that if you don't have at least one side of a triangle, then it's not solvable, right? So this other two examples, C and D, case 3 and 4, two sides, an included angle, and three sides are required for the law of cosines. So let me go ahead and close that. That was from 6.5. So since they say the law of sines cannot be used directly to solve triangles if we know two sides and the angle between them, or we know all three sides. In this case, the two cases of the law of cosines apply. So we saw for the two cases right now before I closed it. And then they say for any triangle ABC, we have the following formulas. So a little bit lengthier. Do you agree? Harder to remember, more stuff to remember. But generally, we usually let some formula sheet. So out of these three formulas here, which one looks the most familiar if I were to cover the -2 2 times the product of the other two sides and cosine of a particular angle? Let's say I cover this, all this right here. Let's say I color. I just, for example, I'm just saying I'm covering that with my hand. Which one looks the most familiar? The last one, right? Right, the last one. So that one looks like the Pythagorean theorem, right? It's pretty much a squared plus b squared equals c squared. So the law of cosines is pretty much a consequence of of the Pythagorean theorem. So there is a pattern there. If you're looking for a particular side of a triangle, it's this, a squared is going to be equal to the sum of the squares of the two other sides minus 2 times the product of those two other sides and cosine of the angle of the particular side you're solving for. So I know that's a rant, but that's the pattern for each particular one if you look at it. So if you look at B, it's b squared is equal to the sum of the squares of the other two sides minus 2 times the product of the other two sides cosine of that angle. And again, I can repeat the same thing for the last angle, the last side as well. So they mentioned this in the next slide that, but the last one, pretty much, if we use a particular angle, the last one will be the Pythagorean theorem. So I believe they state that here. So in words, the law of cosine says the square, so they're just going to repeat what I was saying. The square of any side of a triangle is equal to the sum of the squares of the two other sides minus twice the product of those two sides times cosine of the included angle. That's what I was ranting a little bit earlier. But that was a pattern in each particular formula. Now they say for the last one, if one of the angles of the triangle, say angle C, is a right angle, right, 90-degree angle. Let me go ahead and bring this down. Say angle C was 90 degrees. Angle C is a right angle, then cosine of C is equal to 0, right? So cosine of 90 degrees, that's what they're asking, that's what they're stating. What would be cosine of 90 degrees? I think we hopefully we know that already, or not. Calculator, anybody can tell me that? Cosine of 90 degrees? What would be cosine of 90 degrees? 0, right? Cosine of 90 degrees is 0. So that's what they're stating there. So let me go ahead and erase that, just in case it's getting over the 0. Cosine of pi over 2 is also 0, but we're talking degrees. So cosine of 90 degrees should equal 0. So let's go back to our chapter there. So they're saying if you are particularly working with a 90-degree angle, it says the law of cosines reduces to the Pythagorean theorem. Thus, the Pythagorean theorem is a special case of the law of cosines. Right? All right. So if this happens to be 90 degrees, that would be 0. 0 times all this would cancel out, and that's why they say you'll be left c squared is equal to a squared plus b squared, and that the Pythagorean theorem is a special case of the law of cosines. So very interesting, right? That you've seen that before. But it just builds from there. I mean, like all topics in mathematics, you learn something and it starts just to build and build. So hopefully this is a little straightforward right now as we've seen it, because it looks familiar, like the Pythagorean theorem. And generally, I like law of cosines better than law of sines, because law of sines has fractions in it, but law of sines is easier to remember. Law of cosines is just a little bit longer. But let's go ahead and try working with one of these particular triangles here. I see we have a side case. Side case. So the sides of the triangle are A, B. A is 5, B is 8, C is 12. Okay, so find the angles of a particular triangle. Again, you can sketch it however you like. Just respect, the sides and the angles. So you could have done A, B, C. I know this is not to scale, right? They helped us out with the sketch there. So if you call this A and you want to call this B, I know everybody likes to draw differently. Remember, this would be angle B. So opposite of angle B would be a little b. So this would be 8. This would be 5. And then this would be 12. So again, you can draw the triangle however you like. Just respect, which vertex is A, which is vertex B, and which is vertex C. So I'll go ahead and erase that. I'm just mentioning this. How do I know I need to do A, B, C in that particular way? No. You don't need to do it in that way that they sketch it in the textbook. Just remember, you need to just respect how you sketch it. What is angle B and what is side B? That's all you have to do. Let me go ahead and erase that because their picture is obviously better. Right? So if we get a little sketch, if you feel that you can do better than theirs, right? So they don't get a unit of measurement, but we know how to deal with whole numbers that, obviously 12 is bigger than 8, 8 is bigger than 5. All right. So I know the sides of every part of the triangle. So let's take a look. Let's move on. So I know ABC. So it says, let's find angle A first, right? We could have used anyone. So they went ahead and saved us some time here. You would need to manipulate the formula. I know I did that in 6.5, but here is the formula. Ready? You want to box set it? That's the formula to find angle A for the cosines. So again, if you knew this first one, that I'm just putting a bullet there, you could solve for it. You just subtract b squared, subtract c squared, and then divide by negative 2bc. So that's the formula. All right. And if you do like, after I finish this section, we'll Google it together. If you do have trouble with algebraic manipulation, uh, I'll go ahead and show you the formulas right now in a bit for both respected section 6.5 and 6.6. All right, so here we want to solve for angle A. You could have used this, you could have used A, B, or C first, but let's just solve for angle A, right? So we know B, let me go ahead and jot down what the equal to. Little a was 5, B was 8, C was 12. Right? Let's go ahead and plug in simply as is. Here we get, that's going to be 8 squared plus 12 squared minus 5 squared all over 2 times 8 times 12. Right? This is cosine of A, cosine of A. If you have a nice calculator, it will just plug that in and should reduce to 183 over 192. Right? Or simply you could have just cosine inverse from the get go, right? Cosine inverse. Let me make a new slide. Did anybody else get 183 over 192? Or if anybody got a decimal, something in the negative 0.6875? All right. So I want to leave it as a fraction because when you round before your final answer, you tend to get round off error. So that's why I wanted to leave it as 183 over 192 before I do inverse. So let me make a new slide. So then we have cosine of A equals, that was 183 over 192. All right, to find the angle A, remember we use cosine inverse or sine inverse, depending on what we're working with. So we did sine inverse in 6.5. So here we'll do cosine inverse. Cosine inverse. All right. Let's go ahead and round to the nearest whole angle. Let's go ahead and round to the nearest whole angle here. So angle A. Remember your calculator needs to be in degrees mode. Let me fix that approximate symbol. Did anybody get 18 degrees, approximately 18 degrees? 17.6, yes. So 17.6 rounded up to the nearest whole number. Yeah, perfect. Yes, 17. Yes, awesome. Yes, awesome. Those numbers are good. Those numbers are good. Yeah, because they want us to round to the near. I don't think they stated it, but they're in the solutions. The textbooks went ahead and rounded it to the nearest whole number. So round to the nearest whole number, we should get 18 degrees. Then similarly, let's go ahead and do the same thing. Rinse, repeat. What did I say? Rinse, lather, repeat. So we'll do the same thing. So it's great that they gave us the formulas already for the next two angles. Here we have cosine of B, cosine C. Remember, you would have to do cosine inverse at the very end. So let's go ahead and plug in. Here we have, it's going to be 5 squared plus, so you might as well, if you have a calculator, you can already do cosine inverse, I guess, cosine inverse of cosine of B. Yeah, that's fine. You can put parentheses over it. And if you're liking it, you can do cosine inverse already from the get-go to save you some time, since we like to round off at the very end. I think A was 5, so it's going to be 5 squared plus. This is just to save time, so you don't have to plug it in, reduce, get a fraction, and do cosine inverse if you want to save some time. But be careful with, some of us who have older calculators, they don't make the nice fraction symbol bar. Be careful with your order of operations. So here would get C was 12 squared minus 8 squared all over. That's going to be 2 times AC. So A was 5, C was 12. Right? Now that cosine inverse is going to cancel out with that cosine. We're left with B. And then we do the cosine inverse is simply what we have all there, just to save some time. Take the cosine inverse from the beginning. Again, let's go ahead and round to the nearest whole angle. Anybody get anything close to 30? Something close to 30 degrees? Around that ballpark? 29, yes. 29 was I was looking for something. Yeah, all right. Yes, 29 was what I was looking for. 29 degrees. 29 degrees. We use a different color so we can differentiate from angle B and C. 29, can I get anybody else to second that? 29? Okay, awesome. Perfect, yes. Just so you can get familiar plugging in, as we are in class. Because if you did get something else, let me know. Maybe your calculator's not in degrees mode, or we typed it in wrong. Okay. All right. Perfect. And then now for the last one, let's go ahead and do cosine. To save some time, again, you could have done it the way we did it for angle A. I just reduced the fraction, but to save time, we can also do this, right? So cosine inverse, the cosine of C, cosine of C. All right, cosine inverse, and let's go ahead and plug in. All right, this saves us a lot of time. That's why I like chapter 6. It's that little application problem where we can use our calculator. Chapter 5, yeah, you can use your calculator, but if you know your unit circle, you don't even need your calculator at all. Besides chapter 6, besides the application problems, you definitely don't need a calculator for this class. All right, so cosine inverse, let's go ahead and plug in. A squared, so that's going to give me, what was 8? A was 5, right? It was 5, I think. Yes, 5 squared. 5 squared plus 8 squared minus 12 squared all over. It looks like I'm running a little bit of space there. All right, that's going to be 2 times 5 times 8. All right, this cosine inverse was canceled out with that cosine, and then we're left with cosine, or sorry, we're just left with C, which is angle C. So angle C. So I should have done that for B. I forgot the angle symbol. Then for angle C, this is going to be approximately. I'll give you some time to plug that in. Looking for something around something that's greater than 100. It's going to be our largest angle here. $133. Yes, perfect. It was okay. Awesome. Our largest angle happens to be angle C. All right. Now, I'm sure some of you hopefully thought to yourself, question yourself, why am I doing it for the last one? Right? Isn't the total sum of a triangle 180 degrees? If I know 2, I can just add those 2 and then 180 minus that value. So generally, I would like to do that too, but mathematics likes to make our life more difficult. So we move on to the next slide. We can go ahead and plug in what we found already. We found this to be 29 degrees. And then we found this to be 133 degrees. All right. Now let's say, of course, 2 angles. We found A, B first. So once 2 angles have been calculated, the third can more easily be found from the fact that the sum of the angles of the triangle is 180. However, they say it's a good idea to calculate all 3 angles using the law of cosines. and add the three angles as a check on your computation. So I believe they do add up to 180. So we got 133. Double check. 29 plus 133, and then what was the first one? First one was 18. That's 18. Let's double check. All right. So we have 29 plus 133 plus 18. That gives me 180. Gives me 180. So again, they make our lives miserable. They're like, no, don't do it the easy way. Use the law of cosines. So this one's not too bad. That's not too bad. So um, the others, here we just show this particular case. So the other case would be just as easy as well. So does this seem easier than law signs? Why is it 133? Okay, so let me go back because we just simply use the law of cosines. We use the law of cosines for angle C. Is that what you're asking for? Why is angle C 133? For cosine 0.67, 6775. You mean you got negative 0.6875, right? So go ahead and take okay, yeah, 0.677, yeah, yes. So where they got this number. So I should have deleted that. Um, that number that number is this number. If you were to round it to a few decimal places. So maybe I should have deleted that. Because if you actually get this equals all that equals, I believe it's negative 0.6875. But cosine is an even function. Since you're doing cosine of a negative number, this doesn't matter. There should technically be a negative in front of here. But cosine is an even function, so you can disregard that. That's what we saw in chapter 5. So maybe I should have just deleted that. Okay. Yeah. So yeah, let me go ahead and delete that. I think this would be better. Yeah, like this. Yeah, I'm sure most of you were probably wondering where the hell that came from. And angle B was 29. Yes, I believe. Let me just go ahead and space. All right, I'll leave it like that. I think that's better. And an angle B was 29 degrees. All right. I think that's better like that. So yeah, some of us who don't have fancy graphing calculators, you may have to get a decimal first and then do cosine of that decimal first. So, and the reason why they didn't have the negative in there because cosine is an even function. So I think that now it's a little bit clear. I think hopefully now. So does that make sense now? I think you can unmute yourself now. I think it was off now.
Yes, sir. I understand.
All right, awesome, perfect, perfect. So if you happen to run into the other case, we would just simply just go to this formula and plug in what we have. So this it's not too bad. It's not too bad. So we already have the three. So they gave us these three formulas, and then thank goodness they were nice to us, and without having to solve for ourselves. Or was it? They gave us the other three formulas too. So here we have this formula for the angle A, angle B, and angle C. So technically six formulas. It's technically six formulas. So three. If you can remember the three, you can manipulate them and get the other three that I just boxed in right now. So those are the I guess six formulas we'll be using for this section. So when you do run into the other case in the homework, just use these formulas just like we just used right now. And how hard do you feel this example was? Too easy? Not that hard, right? This one wasn't not that hard. So we just patiently followed me, followed everything I did. That's exactly what we do for these problems. Whatever's given, just look at the formula what you need, which has enough information for you to plug in and just plug in. All right. So that's what's nice. Just see what you have and in which formula. Just look at the formulas and say, oh, okay, I have most of all this one. So I have most of all these information. So I'll go with the first one or the second one or the third one, for example. So just based on the information that's given. So side was pretty straightforward. We do side angle side. I believe it was side angle side. And then here, let's look at area of triangle. This one is very straightforward as well. So here we have a non-right triangle. So an interesting application of the law of cosines involves a formula for finding the area of a triangle from the lengths of its three sides. So uh, two applications we see from a law of cosines case of having all three sides. So this formula definitely is always, this formula is given. It's not very difficult to remember, but here we have a formula and we have S minus A, S minus B, S minus C. So there's some pattern there. There's some pattern there. Uh, but again, there's a lot of formulas in this course, and a lot of math courses, right? So they have S, and we know what A, B, and C are. Little A, B, and C are the sides of the triangle. What is S? So they went ahead and explained to us. So let's say S is one half times the sum of all three sides. So it's pretty much add up all three sides, divide by two. If you multiply by half, it just means divide by two. So that they say that is known as a semi-perimeter. So if you added all three sides of the triangle, you're simply finding the perimeter. So they say divide the perimeter by half, by two. That's simply what S is. Right. So here we have a nice little application problem here. It says a businessman wishes to buy a triangular lot in a busy downtown location shown below in the figure 9. The lot frontages on three adjacent streets. Here we see 120. Well, this street, and this street right there. Uh, and the lot frontages on the three adjacent sides happen to be 125, 280, and 300 feet, respectively. Find the area of the lot. So first things first, let's go ahead and find a semi-perimeter. So that's the first step when you're finding an area, particular triangle. We have a law of cosines application here. So the semi-perimeter is it's the following. So just divide all three sides. 125 plus 280 plus 315 all over 2. So what does that give us? Does anybody get 300, somewhere in the 300s? 360? Yes, 360. Yes. So we should get 360. All right. We should get 360. All right. And then now by Heron's formula. So the formula is actually called Heron's formula. That's a special. That's the formula there. I didn't say it. Sorry. I did not give credit to the gentleman who discovered the formula, proved it. All right. So by the formula, let's go ahead and find the area. They use that nice A-looking symbol. So it was S. So we found S to be 360. If we want to go back, that's the formula. S. And there's a square root. I'm going to do the square root at the very end. And then it's going to be S minus each side, the product, and then multiply each particular value. So here we have parentheses S minus A. So 360 minus A is 125. Times S minus B, but we know S and we know B, right? So that's going to be 360 minus 280, and then S 360 minus C, which happens to be 315, and all square root, all square root. Let's go ahead and round to the nearest whole foot, or the nearest whole number. We're talking area, so square foot. So this one's going to be, a larger value than the ones that we were working with in the first example. But here we get something in the 17,000s. This one we don't need to worry about our calculator being radians and degrees. So be careful when you do have a trig function. Yes. So you want the easy way to remember if you to be in degrees or radians is, are you working with something in degrees? So if you're not working with anything in degrees, then it should always be in radians. So be careful. Be careful with that. Be careful with that. So if you know it's an application problem that involves degrees, then change it to degrees. If they're not talking about degrees, 360. Anybody get 17,451.64? Yes, awesome, awesome. Let's go ahead and round perfect. That is perfect. Let's go ahead and round to the nearest whole number. So I believe 452, and then we're talking feet, so feet squared, right? Feet square feet. So thus the area is approximately 17,452 square feet. All right, and I believe this is our last slide for this section. This section is nice. Oops. Short section, sweet. So I'll go ahead and put that online after sometime after 12, after the second class. So if you haven't taken a look at the law signs, I would go ahead and take a look. From the looks of it, it looks like some students did well on it. Everybody had, the ones that had finished already had the 100. So that's a good sign. That's a good sign. So when you try out law of cosines, you should more likely breeze through it if you already have the 100 for the law of sines. So any questions, comments, concerns before I close this and we go into 7.1? No questions, comments, concerns, worries? All right, all right. So hopefully everyone felt like this was the easiest part that will be on exam 2, because we are done with chapter 6. We'll be moving on to chapter 7. So let me go ahead and save this file. Save it as, right? Go ahead and save this on the desktop, and we'll name it today's date. which is the 12. Perfect, perfect. All right. So 7-1. Stop me anywhere. Stop me anywhere you think it's. Not this one. All right, now I need to. I think I need to download it real quick. So I think all the materials already. Yes, everything should be uploaded. All right. So let me go ahead and pull up chapter 7, section 1. We got 5 sections here. So this one's about 20 slides, I believe. This section is not too long. All right. So this section is known as analytic trigonometry. So like I said, this is 22 slides. So you can minus this one, you can minus this one, you can minus this one. So objectives is simplifying trigonometric expressions, which is very important not only in this course, but as you move on to pre-cal. Now cal 1, now it won't be the main idea, but it might be part of solving a particular problem, right? And proving trigonometric identities. So you don't really prove that many trigonometric identities unless it's a proof-based calculus course. Uh, Maybe you'll take a look at it, but I don't think they'll require you to prove that much, depending on what institution you plan to go on. Especially if you don't take Cal 1 in high school and you take Cal 1 in your particularly respected school you go to. So it can be taught differently. All right, so more formulas as we usually see in mathematics. All right, so we should be familiar with some of this already. We should already be familiar with reciprocal identities, which we already saw in chapter 5. We've looked at Pythagorean theory, Pythagorean identities, I think twice now already. I think it's popped up in chapter 5, popped up in chapter 6 as well, I believe. So we already taken a look of this. We've seen this. We've seen even odd identities. There wasn't much to play with. We saw how it was being used in the textbook for the last example, not the area example, but the first example we saw in 6.6 when we got a cosine of 0.6875, I believe. They took out the negative because it was 0.6875. Yeah. So we've seen those three first. So we've seen that sine and tangent are odd functions. So if you're evaluating a sine of some negative value, they say you can just pull the negative out. That's why the negative is right there. As for cosine, they say if you're evaluating the cosine of a negative, you can just disregard the negative value. So we briefly looked at those. Maybe you played with that more on unit, but it wasn't too much of a hassle, right? Because once we already knew what x was, we pretty much knew how to evaluate it. What's new is the cofunction identities. Now, since it is new, I generally don't. To be honest, I don't recall using cofunction identities that much. Maybe once, maybe twice. So if needed, we'll come to this cofunction identity. Maybe later on in this chapter. I don't recall. I think it comes up maybe once, or I don't recall. So if needed, we'll come to the cofunction identities. But for the most part, we will work with the first three that I just checked right now. Okay, heavily, not heavily on this, but definitely when there's nowhere else to go, that's what we'll be using. So, and we're going to see that on the first example. Hopefully, it's not too vague. All right. So, all right, let's take a look here. Let's take a look at the first example here. So, all right, so we're going to have to use the one I just circled in the first example. So, Hopefully, we were able to get through the first example. Not too many question marks, um, but let's take a look. So we have some information first. They mention identities enable us to write the same expression in different ways. So it's often possible to rewrite a complicated looking expression as a much simpler one. To simplify algebraic expressions, we use factoring, common denominators, and special product formulas. So to simplify trigonometric expressions, we use the same techniques together with fundamental trigonometric identities. So trigonometric identities and a lot of algebra. Uh, so if I'm doing a lot of algebra, stop me because I know algebra usually is tends to be our weakest spot. Because yes, we learn algebra and it, do this, do that, do that. Um, but that tends to be the harder part for students to understand. It will be one or two steps of pre-algebra or or sorry, one or two steps is pre-cal, and the rest would be college algebra material. Not college algebra material, but pure algebra, just techniques. Which we after the end of the course, I'll be honest, I'm not a master of every course that I took, but it takes some time. It takes practice, so that's why I spent a lot of time outside of class reading. But let's get through. Let's pull this bandit off, right? Let's pull this bandit off and let's get ready. Let's look at the first example. So let's go ahead and take a look here. Now they want us to simplify. These are a little bit more harder when we don't know what to prove, or we don't know what to simplify our expression to. So those are a little bit harder, but we do have a rule of thumb. When you do have an example that want us to simplify the expression, generally they like to simplify it to one trig function. So first step first is they want you to rewrite everything as much as possible as sines and cosines. So here they want to start by rewriting the expression in terms of sines and cosines. So I have cosine t plus tangent t times sine t. So first is first, when you're simplifying expressions, wherever you see a tangent, turn them into sine and cosine. So that's usually the big hint, and you're gonna want to use the reciprocal identity. So what is the reciprocal identity for tangent? Which one do you think I can use from the first check mark? What is tangent gonna equal to if we use the reciprocal identity? Is it possible to rewrite tangent as sine over cosine? Yes or no? Do they say tangent is equal to sine over cosine? Haven't I mentioned that more than once? That tangent is the ratio of sine over cosine? Okay, yes, awesome, awesome. All right, perfect. All right. So that's not too new, right? This is already I mentioned it before. Okay. All right. Perfect. Perfect. All right. And the others should follow as well, right? I've also mentioned that secant was 1 over cosine, cotangent was that, but the one we're working with is the one that's underlined. So let me finish doing that. That's the one we were working with. So let's go ahead and rewrite tangent as sine over cosine. And with respect to they're using t instead of x. So they're just using a different variable. So let's go ahead and just respect that. So they're using t instead of x. So here we have cosine t. I'll curve it because my t's look like plus signs. And then plus tangent. Remember, tangent can be rewritten as sine with respect to the sine of t over cosine of t. I know it looks coast. It doesn't look that great when you don't put parentheses. That's why I like putting parentheses. Then it ends up being too many letters. Preference. It's all on preference. Preference of the maybe you don't like parentheses, so you may rewrite. You may write it without parentheses, but I see too many letters. I have to put my parentheses, and then my reciprocal identity. I'm still missing times sign. I want to push that to a little bit to the side. Can I? Just so I can have a little bit of space to write times sign of t. So I probably got to move the others as well. But I don't got to be constrained. I can put equals over here. I don't got to be constrained to that. I don't have to be constrained to only this part. So, all right. So let me go ahead and rewrite this again. So cosine t plus sine of t over cosine of t times sine of t. All right, so they give us a little bit of hints on the right-hand side. They say common denominator, common denominator. All right, so before we do that, I might make a new slide. All right, before we do that, let's go ahead and multiply this fraction. Can we multiply it? What would be sine? Would sine times sine be sine squared? Wouldn't it? Here we have cosine t. Right, when we multiply fractions, you just multiply the top parts respectively, the bottom parts respectively. Sine times sine would be sine squared. Cosine of t times 1 is cosine. Right? Right. All right, so let me make a new slide. Let me copy and paste that. Let me copy and paste what I just had. That was cosine of t plus, I think it was sine squared uh, sine squared of t over cosine of t. Now, I know I ran out of space here, but the next hint was common denominator. Common denominator. So we want to write this as one fraction. So I know cosine, his denominator is 1. So in order to write them as one fraction, they need to have the same denominator. So can I multiply cosine by 1 in the form of cosine over cosine? That makes sense? Multiply this by cosine of t times cosine of t. So cosine times cosine, that's going to be cosine squared. So I'll write cosine squared here, cosine squared of t. Cosine of t times 1 is cosine. Plus sine squared of t over cosine of t. Now that they have the same denominator, I can go ahead and rewrite this as one fraction. And then I'm just going to go ahead and bring the two numerators together and respect it as a plus between them. So this would be cosine squared plus, oh, don't forget my variable, plus sine squared of t. All right. Now, do you see where we're going to use the next identity? Or what identity? Let's go back. Let's go back and see. They gave us a hint. Pythagorean's identity. Pythagorean's identity. Let's look at that. Let's look at the one that I just circled. Sine squared plus cosine squared. Do I have that in my particular problem that I have? No, it's the same, virtually the same thing, right? So doesn't matter the order in which you add them. But doesn't that equal 1? Doesn't the top part equal 1? All right. cosine squared. I'll do a little cosine squared plus sine squared equals 1, right? Doesn't that equal 1 from the Pythagorean identity? No, it's rewritten the other way. It's the same thing. Sine squared plus cosine squared or cosine squared plus sine squared is equal to 1. So let me go ahead and replace all this with 1. Here we get 1 over cosine of t. And then I can use one more reciprocal identity, and that's 1 over cosine. I'm going to go back. If you're not familiar with, that's secant, but 1 over cosine is actually secant. So I'm going to go ahead and write that 1 over cosine is equal to secant. So ultimately, if you think about it, what we started with here in the bold or in the dark in the regular color ink. So here, cosine t plus tangent times sine actually just equals secant. They're the same thing. They're the same thing. So here we are able to simplify a trigonometric expression. So from an expression that involves 3 trig, right? It has 3 trig. It has cosine, tangent, and sine, right? It's got 3 trigs there. So we see that simplifies to simply just secant, and we are done, right? So these problems are a little bit more difficult because you need to know how to get to, how this equals to secant t. So someone asked me one time in a previous pre-cal, so secant's the answer, or if cosine's the answer, whatever trig function it simplifies to. I was like, well, technically, yeah, yeah, it's secant's the answer, but on a written exam, it's a little bit different on the online, right? So I'll be taking a look at how that homework is. But at least for 6.6, that should be a little easy. But they asked me, so what's the answer? And I'm like, well, this is a written exam. It was when we could still meet. And I told them, well, you have to show me everything in order for it to be right. So that's why I said this chapter, whenever they ask us to do prove or simplify, you need to show every single step. So it's kind of hard to wing these type of problems. It's kind of hard to wing this type of problems, right? Because you have to show every single step how you got there. So do we have a little bit of information before? So no, we go into proving trigonometric identity. So simply we did it. This is simply a proof. It was a simplification, but we didn't know where we were going to. So if they had put that it equaled secant from the get-go, we could have gone from the left-hand side to the right-hand side. So we'll see what that means as we get to proving trigonometric identities. So we'll talk a little bit about this. This is at 10:30 already. So I at least want to get to slide 12. And then we'll recite these steps on Wednesday. All right, so now proving trigonometric identities. So an identity holds for every single value that you can pick for the variable, right? If they say x equals 1, for example, let's go back to our formulas. For example, the one that right here, sine squared plus cosine squared equals 1. For whatever values I pick for x, it's always going to equal 1 no matter what. No matter what values I pick for x, sine squared of x plus cosine squared of x always equals what? X no matter what. So that's what makes it an identity. It's true for all values of x. So I think they want to show us that the idea that some identities, you can write a series of trig functions or trig identities, and assume that to be well, I shouldn't say identities. You can write a few trig functions, cosine, tangent, secant, throw some together, slap them together, and call it an identity. But unfortunately, if they can prove that it's not one, and then unfortunately it won't work. So I think they want to give us the idea here. So it says many identities follow from the fundamental identities that we'll be working with from that blue box that I've been moving back and forth to. On the examples that follow, we learn how to prove that a given trigonometric equation is an identity, and in the process, we see how to discover new identities. First, it's easy to decide when a given equation is not an identity. All we need to do is show that the equation does not hold for some value of the variable or variables if there's more than one, and we'll see that in the next step here, which is sine x plus cosine x equals one. So they went ahead and took the square away. Went ahead and square away, so they give us one of the most basic examples. So let's go ahead and choose x to be pi over 4. Let's say x is pi over 4. If you're in degree modes, that would be equivalent to 45 degrees. So pi over 4 is equivalent to 45 degrees. So let's go ahead to see if this equals 1. This is how you can simply just show if a trig identity or if identity is not an identity by simply just picking a value. For x, they happen to pick pi over 4, 45 degrees. All right, sine of pi over 4 plus, what was that? Plus cosine of pi over 4. All right, let's see what that equals to. Right, sine of pi over 4. I like working with pi over 4 because the terminal points are pi over 4 is square root 2 over 2 and square root 2 over 2. So for sine and cosine, you should get square root 2 over 2 plus square root 2 over 2. All right. You can plug that in your calculator if you like. If you're not, again, I can pull up the unit circle. Let's pull it up. Pi over 4 is about 45 degrees. The terminal points are square root 2 over 2 for both x and y. So here, you can see if you have trouble, especially if you're scared of square roots and fractions, you have half of a square root 2. You have half of another square root 2. Doesn't that together make a whole square root 2? Right? Again, if you are afraid of square roots and fractions, you can simply just plug it in. You should get square root 2, which does not equal 1, which does not, so you put it equals with a line and a symbol. That means does not equal 1. Does not equal 1. So to verify the trigonometric equation is an identity, we transform one side of the equation to the other side by a series of steps, each of which itself is an identity. So basically, kind of what we saw in example 1. You transform one side of the equation. We didn't really have two sides of the equation, but we're able to transform parts of the expression, so we had terms to simplify, which is ultimately the same idea when we're proving. We're gonna use trigonometric identities to transform one side to the other. So they have a series of steps here, but we won't be able to get. I don't want to, I do have enough time, but just so it can be fresh, fresh for Wednesday. We did a little bit of chapter 6, got a little bit of taste of 7.1, about halfway done. So definitely we should get into 7.2 on Wednesday. All right. So here are 3 steps. They say for proving a trigonometric identity. So we'll see that on Wednesday as we transition to the week. So they say step 1, start with one side. Start with one side. Because now we have an equal side. We're going to have an equal side. We're going to have some stuff here and some stuff on the right-hand side. So this is left-hand side, right-hand side, right? Pretty easy. So that's what they say. Start with one side, either the left or the right. Left-hand side or right-hand side. Pick one side of the equation and write it down. Your goal is to transform it into the other side. It's usually easier to start with the more complicated side. For example, if we in example 1, the first problem, we started with a more complicated expression, and we simply ended up with secant. So start with the one that looks more complicated. Use known identities. Use algebra and the identities you know to change the side you started with. Bring fractional expressions to a common denominator. Factor and use fundamental identities to simplify your expression. Convert to sines and cosines. So that was the first step we did in the first one, and we actually did some algebra and common denominators too. So step three says convert to sines and cosines. If you are stuck, you may find it helpful to rewrite all functions in terms of sines and cosines and try to combine like terms. See if you have some sines squared plus cosine squared and common denominators and whatnot. So depending on what you have. The first example we'll be seeing on Wednesday is this one right here. All right, so we'll leave that to Wednesday. I'm sure you may be already exhausted some of your brains right now, so we'll leave that to Wednesday. How do you feel about that? I'm sure everyone agrees with that. Is everybody still with me? Yes. All right. Okay. Great. Great. So far, so good. Well, how was the first example here? All right. So yes. So we'll leave this for Wednesday. So we're done for today. So we'll pick up on slide 13. So how was the first example here in chapter 7? Do you already fear a little bit what's coming in the following sections, or do you feel this is different but somewhat manageable? Give me. I believe you can speak up. Let me know how you feel about this. So I'll save this. This was slide 13. Manageable. Yes. Yes. So I'll pick. We'll see how exam two. I'll try to make it as manageable as possible. Not to, because some are easy, some are hard. I'm sure you can already get an idea that some or some can be manageable. I guess we'll use that word. Some obviously are manageable to our strengths right now. So don't get me wrong. There are some that are that I've gotten caught up on. Some I can say that may have taken me 20, 30 minutes just to do one. So I'll make it manageable. We'll make it something that's doable, something not that complicated for the exam. So that's the most important part. We have all this time to do homework, but from an exam time, we're limited, right? So all right, so we'll pick up on slide 13. Looks like we're done for today. So here we'll be able to prove we'll prove our first identity on Wednesday. So be on the lookout later on today for 6.5 and 7.1. I'll take a look at it. I'll take a look at it, and we'll see we'll play it by ear from there. So start with 6.5. If you haven't started, use that as a building guide as you go into 6.6. Because if you understand 6.5 generally well, 6.6 is going to be super easy as well, and then 7.1 is chapter 7 is a different ball game. So we got to change our mindset when we get to chapter 7. Right? No, we're no longer playing with. We will play with some triangles. I think. Yeah, I think so. So I'm not too sure. I can't remember. I know we will start. I think so. I can't remember. We'll see from there. All right. So I know some examples in this chapter are really lengthy, so I might have to skip an example or two. I don't know what section, but yeah, those are. I believe those are not the ones. Those are the ones that are a bit not manageable within a certain amount of time limit. So um, I think that's good for today. We have a few minutes.